This video focuses on some problems involving Newton's law of universal gravitation. So students, stick around, watch and learn. What is Newton's law of universal gravitation? According to this law, every particle in the universe exerts an attractive force on every other particle. A particle is a piece of matter small enough in size to be regarded as a mathematical point. The force that each exerts on the other is directed along the line joining the particles. So consider the two particles with masses m1 and m2, and they're separated by a distance r. We say that particle 1 attracts particle 2 towards m1 with a force equal to F directed to the left. At the same time, particle 2 also attracts particle 1 with an equal but opposite force F, of course, towards the right. So the equality of these two forces is based on Newton's law of interaction. In other words, the two forces that are labeled here, positive F and negative F, have equal magnitude, opposite in direction, and are acting on two different bodies, and they occur at the same time. The law of universal gravitation can be summarized in this equation, F, which stands for the force of gravity exerted by the two particles. And this is equal to a constant, capital G, known as the universal gravitational constant, multiplied by the product of the two masses, m sub 1 times m sub 2, and divided by the square of the distance that separates the two particles, or r squared. The value of capital G is equal to 6.673 raised to the negative 11 Newton meter squared per kilogram squared. As an example, supposing particle 1 has a mass equal to 12 kilograms and particle 2 has a mass equal to 25 kilograms, and the distance between them r is equal to 1.2 meters. So using this formula, we just substitute the given capital G, which is 6.67 raised to the negative 11 Newton meter squared per kilogram squared times 12 kilogram and times 25 kilogram divided by 1.2 meters squared. And simplifying or doing your math, we will arrive at this value for the gravitational force of attraction between these two particles, which is 1.4 raised to the negative 8 Newton. Now this amount of force, we say, is a very small amount of force. This is not surprising because of the um, small, relatively small masses of the two particles, 12 kilograms as well as 25 kilograms. We will also look at a situation where the magnitude of this gravitational force can be extremely large. That is, if we are talking about extremely large masses as well. As our second example, we have the Earth and the Moon are exerting a mutual force of attraction as shown in this diagram, right? So we need to know how far the Moon is from the Earth, but this time we will be considering the distance r, okay, from the center of the Moon to the center of the Earth, okay? Unlike in our first example earlier, when we were talking about particles which we assume to be a mathematical point, meaning dimensionless, I should say, dimensionless particles. But this time, we are talking about heavenly bodies, right? The radius of the Moon and the radius of the Earth are such large distances, and we need to consider them in defining the distance r, right? So using still the same formula for the law of universal gravitation, all right? So we substitute in the equation the value for capital G, and the mass of the Moon is known to be equal to 7.3 raised to the 22 power kilogram, while the mass of the Earth is 6.0 raised to the 24th power kilogram. And the distance r between their centers is known to be 3.8 raised to the 8th power meter. And then you got to square that. So again, doing your math, we will arrive at the value of the gravitational force between the Moon and the Earth, and that is equal to 2.0 raised to the 20th power Newton. And as you may notice, okay, the order of magnitude of this force is times 10 to the 20th power Newton. So it is such a large gravitational force, which again uh, is not surprising because we're talking about large bodies such as the Moon and the Earth. Okay, so if the two bodies involved are such huge bodies, such as heavenly bodies, there is a need for us to know their what we call radii. Okay, the radius of the Moon and the radius of the Earth, okay, have to be considered as part of the distance small r. We now have our question number one, which is a conceptual question. By how much does the gravitational force between two objects decrease when the distance between them is doubled? or tripled, or increased tenfold. So our answer for the first question, when the distance between them is doubled, we say, since the force F is inversely proportional to the square of the distance that separates the two objects, then we say that F is going to be quartered if the distance d is doubled. Alright? So, we simply do this simple mathematical illustration or computation. Alright? So, what we do is we just uh, follow the formula for F. Alright? All other factors held constant except for the distance. Okay, when it is doubled, then all you have to do is use the formula 1 over d squared. Alright? And the square of 2, of course, is 4. But F would then be equal to 1/4, meaning the new force will just be 1/4 of the original. Alright? Now, for the second one, what happens if the distance is tripled? If the distance is tripled, we say that the F is reduced by 1 over 3 squared, and that is 1 over 9. So there is a decrease in the amount of force by as much as, or we say that the new force will just become 1 over 9, the original force. Finally, if the distance is increased tenfold, what will be the new force? So again, following the expression, F is directly proportional to 1 over d squared. So we just substitute for the distance d, okay, the value which is 10. That's the meaning of tenfold. The distance will be increased by 10 times. Alright? And as a result, 1 over 10 squared becomes 1 over 100. In other words, the new force F, okay, will just be 1 over 100 times the original force. Our next conceptual question, question number 2. Consider a mango at the top of a tree that is pulled by Earth's gravity with a force of 1 Newton. If the tree were twice as tall, would the force of gravity be only 1/4 as strong? Defend your answer. Okay? So based on the relationship between F and the distance R, okay, we say that the F is inversely proportional to the square of the distance R. That is why in the question, if the distance d is doubled, all right, we might think that the force will decrease by as much as 1/4 of its original force, okay, when the mango is at the Earth's surface. Okay, so how are we going to prove? Okay, if you say yes, it's going to be 1/4, or if you say no, it's not going to be 1/4 as strong, then you have to defend your answer. All right, so the correct answer is no. It's not going to be 1/4 as strong. All right, the force of gravity will become 1/4 as strong only if the mango is brought to a height equal to twice the Earth's radius. So the formula for universal or gravitational force, okay, defined by Newton's law of universal gravitation, we say that any object on the Earth will have their maximum force of attraction from the Earth if the object is located, okay, at the Earth's surface. Right? So, if the object is moved to a greater distance from the surface, or if it's going to go to a higher altitude, okay, the height okay, has to be at least twice um, the value of the Earth's radius, right? Uh, Considering the height, all right, the height of a tree, which normally is 20 meters. So if you're going to make it 40 meters, all right, and knowing that the Earth's equatorial radius is about 6,378 kilometers, while its polar radius is about 6,357 kilometers, all right, whichever you are going to take as the value for the radius, or better yet, we take the average, all right, by just adding this to divide by 2, but still, you will find out that compared to that radius or average radius of the Earth, all right, multiplying the height of a mango tree by 2 will just make it 40 meters. And 40 meters is just about 0.00063%, okay, the value of the radius of the Earth. It's too small to have any significant change in the weight of the mango. So this question is similar to other questions. Say, for example, do you really expect that you're going to climb stairs, okay, walk from the first floor up to, say, the 20th floor, okay, of a typical skyscraper, okay? Do you really expect that your weight is going to decrease significantly? Of course not, all right? Because as explained here, you will only have a significant change in your weight. We call it now as an apparent weight, okay? The actual force of gravity exerted by the Earth on you is what we call the true weight. But if you are located, for example, at a certain altitude equal to uh, the radius of the Earth, then that's the only time when, all right, when your what do you call this? Your apparent weight will become significantly smaller, right? Then another question that is worth analyzing as well is what would happen to your weight if you're going to go deeper or as you approach, assuming it is possible for you to uh, go deeper into the Earth's center. Just it is just an assumption. All right. What do you think will happen to your gravitational attraction of the Earth on you or your weight? So again, we say that your weight will also decrease. All right. It will also decrease in as much as the maximum weight that you will have is if you are located, okay, at the Earth's surface. All right. So going deeper into the Earth's interior, right? Theoretically speaking, if you are at the very center, then you will be, or you'll be experiencing zero force of gravity because at the very center, all the vector forces exerted by the Earth, okay, part of the Earth that exerted above you, right, will be cancelled by the force of the Earth's gravity below you or at your bottom, and the force of gravity to your right is just cancelled by the force of gravity to your left, all right? But of course, that analysis assumes that the Earth is a perfect sphere with a uniform density. Truth is, the Earth is not a perfect sphere, right? It is its radius, or what we call equatorial radius, okay, is greater than its polar radius. So we say that the Earth's shape is that of an oblate spheroid, right? Moving on to our next question, question number 3. The value of g, or acceleration, due to the Earth's gravity at its surface is about 9.8 meters per second squared. Question letter A, what is the value of g at a distance from the Earth's center that is 4 times the Earth's radius? Letter B, what is the weight of a 75-kilogram astronaut at this altitude? So our answer for letter A, since g is also inversely proportional to the square of the distance from the center of the Earth, multiplying the distance d by 4 makes the g decrease to 1 over 4 squared, or 1 over 16. And 1 over 16 of 9.8 meter per second squared, of course, is equal to 0.61 meters per second squared. And for question letter B, what would then the weight of a 75-kilogram astronaut at this altitude? So we just use the usual formula that relates the force of gravity, or the weight, to its mass. W is equal to F, or is equal to mg. Substituting, we have 75 kilogram multiplied by the computed value of g, which is 0.61 meter per second squared. So we get the apparent weight of the astronaut to be 46 newtons. Question number 4. Calculate the force of gravity between the Earth, whose mass is equal to 6.00 times 10 to the 24th power kilogram, and the Sun, with a mass of 2.00 raised to the 30th power kilogram, assuming that the distance between the center of the Earth and the Sun is equal to 1.50 raised to the 11th power meter. All right, so our computation, again using the law of universal gravitation, capital G is 6.67 raised to the negative 11 Newton meter squared per kilogram squared, multiplied by the mass of the Earth and the mass of the Sun, then divided by the square of the distance r that separates their centers. So doing our math, we will get this value for the gravitational force equal to 3.56 raised to the 22 power Newton. We're down to our last question, number 5. Titania, the largest moon of the planet Uranus, has 1 over 8 the radius of the Earth and 1 over 1,700 the mass of the Earth. Question letter A. What is the acceleration due to gravity at the surface of Titania? And question letter B. What is the average density of Titania? Let the radius of the Earth, arcs of E, equal to 6,370 kilometers, and its mass, ME, equal to 5.97 raised to the 24th kilogram. We are using a more exact value for the mass of the Earth to 3 significant digits. Alright, so our solution to the first question, using the formula for determining the acceleration due to gravity of a planet, we label it as A sub g. It's equal to capital G multiplied by the mass of a heavenly body such as this moon of planet Uranus. All right, then divided by the square of its radius, r squared. Substituting, capital G is 6.67 raised to the negative 11 Newton meter squared per kilogram squared. And then the mass of the Earth multiplied by 1 over 1,700, because the mass of titanium is said to be just 1 over 1,700 times the mass of the Earth. And then divide it by the radius of the Earth, which is 1 over 8. Okay? 1 over 8 multiplied by the mass by the radius of the Earth is the radius of Titania. And then square it. So doing your math, we will get the value for acceleration due to gravity of Titania to be 0.369 meters per second squared. And finally, to calculate for the average density of Titania, we base it on the formula for the density of um, a spherical body. Okay, we assume that the shape of titania is that of a sphere, and since density is mass divided by the volume, right? So we just substitute the mass of titania, all right? Or 1 over 1,700 multiplied by 5.97 raised to the 24th kilogram divided by 4 over 3 pi times the cube of the radius of titania, which is 1 over 8 multiplied by the radius of the Earth. All right. Incidentally, the volume of a sphere is 4 over 3, or 4/3 pi r cubed. That's why we have here the constant 4 over 3. And then the value for the pi, which is 3.14, to 3 significant figures. Right? And then you're going to cube this 1 over 8 multiplied by the radius of the Earth. Okay? So simplifying or doing your math, we will arrive at a value for density. All right. So for checking, I wrote here first the result of multiplying the numerator, which is 3.51 raised to the 21st kilogram, and the result of multiplying uh, the quantities in the denominator, which is 2.11 raised to the 18th power meter cube. Simplifying further, we will get the density of titania to be 1.66 raised to the third power kilogram per meter cube. This value of titania's density is less than the density of rocks here on Earth. Okay, and this is one piece of evidence to prove that titania, okay, the moon of the planet Uranus, is made primarily of ice. All right, so that ends our video tutorial for this topic. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.